focused on this tube along here. And there's quite a bit of technology that goes into building these things. It looks simple. It's like, as a kid, you took a magnifying glass and set fire to paper. It's the same idea, but there's still a lot of technology involved in it. And some of the most interesting things are to do with the materials that are used. The material that's used in this tube is designed so that it absorbs heat and light in the visible range, but it doesn't re-emit in the heat as heat. So it's got a different emissivity in the visible to in the infrared. That way, in the infrared it looks like it's shiny, like aluminium shiny, but in the visible it's very black. So in the visible it soaks the heat up, but in the infrared region where heat is radiated, it doesn't radiate. So it's a special material, and there's been a lot of work done on making those coating materials for the tube, for the tubes, the absorber tubes, collector tubes. The other problem with this, though, is you're sending, in this case, high pressure steam. This is a steam generating solid trough. High pressure steam along this pipe starts off as water and then builds up eventually to high pressure steam, and then you want to drive it through a turbine. These troughs have to rotate, and so there are seals here where at the pivot point which have to rotate, and they have to withstand the pressure and also not leak. So it's quite, and it's hot. It's hot. It's up to 600 degrees. So it's quite challenging, especially the sun being a tricky thing that it is. Sometimes clouds come across and your temperature drops. So you get a lot of thermal expansion contraction in these joints, which is actually unavoidable. So it's quite a challenge for materials to be able to handle that. Another alternative is to use molten salt as a transfer medium, and it's not as challenging as steam, but surprisingly molten salt is amazingly runny, and it tends to leak too. You get these amazing salt drips coming out from the joints, forming stalactites at the bottom, which is very pretty, but it's rather irritating. So there's a lot of materials problems with this technology. It's the most tested technology. And this is what bankers have been investing in, because you can rock up and say, how much is it going to cost and who's going to build it for me? And the answer, you can get an answer to both of those questions. And so it's something that bankers are investing in at the moment. It isn't really, I would guess, this is quite an expensive technology, especially the way it's done right now. And in the future, I don't think it will be exactly like this. I suspect there'll be other ways of doing it. But at the present time, this is the most tried and tested type of solid concentrator, and that's what most investment has been in the recent years. Another type of, similar to the trough collector, is a Fresnel lens collector, an Australian invention invented by academics at the University of Sydney. It's similar in the sense that it tracks the sun in one direction. At the moment, these mirrors are upside down, facing away from the sun. But what happens is these individual, I've got mirrors on them, individually these little flat plates or slightly curved, I think they are flat actually, flat mirrors, track the sun and reflect up onto a mirror, secondary mirror, which is a curved mirror, which then concentrates onto a collector tube. It's cheaper to build because you don't have to take this great big parabolic dish and rotate it. It's not quite as efficient because you've got double reflection, which loses some energy. But there's a commercial installation. In fact, there's at Linsfield in New South Wales, there's one in operation right now, which supplies supplementary heat to a steam-generated, coal-generated steam power station. So the third technology, which I wanted to mention, was the Stirling engine, which is a dish technology. And this, of course, it wouldn't work if it was like this. This is upside down in rest position. It has its parabolic mirror at the top, which is normally the other way around, and a collector which has a Stirling engine in it. And a Stirling engine is just and also an electric motor, electric generator. So a Stirling engine is a very effective heat engine that just works straight off heat. And it's usually a double piston system with a cold end and a hot end. Invented in the early ages of steam. It's been around since the early ages of the steam engine, and it was always a poor cousin to the steam engine until quite recently, where it's been where the engineering skill has come to a point where you can engineer or polish the pistons to such a high tolerance that it works a lot better than it used to. You just need very good tolerances to make it work effectively. And now that the machining and engineering is better, this Stirling engine technology has come into its own. So it's a good standalone kind of system. It really competes with photovoltaic in that respect. You can take this system and put it out somewhere, move it somewhere and just generate electricity straight from it. So it competes in that respect with the photovoltaic industry. The third technology I want to talk about is the solar tower technology, which uses a field of mirrors to focus heat on a small point. And this is solar tower with just one mirror focused at it, so it hasn't got a lot of, it's not actually being used, it's just being tested at the moment at that. The heliostat field is a whole stack of mirrors which focus up at the tower. So this is looking down at the heliostat field, as you can imagine. It's not pointing the sun at me right now. I'm going to take the photo. So all the mirrors are in fact upside down, except for one. They're all in the rest position. And when you look at some of these mirrors from below, this was a system built in the 80s, in 1984 or 85. It's in Plataforma de Sol de Almeria in Spain. These mirrors, or the tracking system, is built to a military standard and very expensive. So obviously you wouldn't want to build a commercial system this way. You need to find a cheaper way of making it. So, but these systems that are in existence and are being used and tested right now are probably over-engineered compared to where we want to be in the future. As I was saying, the sun doesn't always shine. Not only does it not shine at night, but sometimes it doesn't shine in the day either. And this is a graph of solar irradiance versus time. At 9 in the morning, you've got about something like just over 400 watts per square metre of irradiance, solar irradiance. Up around noon, we're getting up to about 750. The maximum you'd normally get from the sun at the equator would be 1,000. But if you're not at the equator, you wouldn't, and depending on what time of year, you don't get that much. On this day, coming up to 750 watts per square metre. At least it was until the cloud came across, and then all of a sudden, your heat energy drops, and it's quite unpredictable as to how it's going to perform. So in this case, you really need to store this energy. Because if you don't store it and you're trying to run a power plant from this, if you're trying to generate steam or whatever, then it's not going to work very well if the temperature keeps fluctuating wildly. So you definitely need storage, even if it's only short-term storage, to get over these clouds drifting across to even out the temperature of your operating plant. However, it's cheap to store heat energy. So and I'll give you some examples of technology that's been operating to give you the top end, which is the really most difficult area from the point of view of making it work. And these are two technologies I'm going to talk about where they're operating at 1,000 degrees Celsius. So it's quite challenging on everything to make it work at that temperature. And what they're using in this case is air as a heat transfer medium. So this is a schematic, and I mentioned this from Solar Plataforma, from Plataforma Solar de Almeria. They have an air collector which collects the air, and it can either go into a storage, transfer heat with a storage tank, or it can run a steam generating plant. Just goes through a heat exchanger and it runs a steam generator. So that system can keep going when the sun's not shining for a certain time. So that's the schematic. But what do the little bits actually look like? Well, what that collector looks like is this one block, 150 mil by 150 mil. There's a whole series of blocks in the collector, but one of the blocks looks something like this. It's silicon carbide, so it can handle high temperature, and it's got all these holes in it, and also the holes are designed so that they get bigger as it goes towards the back, so that you can get expansion. So the cool air comes in and it expands as it comes out the back and is heated up by the sun. So the sun shines through onto the front here, front surface, and heats the front surface, and then silicon carbide's got a fairly good heat conductivity, so it heats in fact the whole block. And then the air is pushed through to heat the air. So the solar collector sits up on the tower, like right at the top here. This is the tower here, and right at the top is the solar collector. There's a whole lot of these silicon carbide blocks in it, and the air is pushed through, and there's a window in front of it, which helps to keep the air in, and so then it generates. That's how it generates the air. The air takes the temperature and takes it off to run a steam generating plant. That's one option for using concentrated solar at high temperature.